Hello. In this video, I will discuss or will formulate the Schrodinger wave equation. This is very much important in quantum mechanics, and whole quantum mechanics purely depends on the Schrodinger equation. In 1926, Schrodinger considered that if a particle has wave properties, that is actually matter wave, there should be some sort of wave equation which can describe the space-time behavior of quantum mechanical particle. Which type of particle is this? It is subatomic particle like electron, proton. So we can say the Schrodinger wave equation describes the behavior of wave function, that is space-time behavior of moving atomic particle or subatomic particle associated with matter waves under different physical situations. That's mean if an electron is moving, so its space-time behavior means at any time in where it is, that is where it is, I will find or we can find it at any time, at anywhere. That's mean space-time behavior, and by which we can get the probability of finding of subatomic particle, and the probability may be varies with its space. Though overall space, the total probability must be 1. This wave equation can be developed both for the time dependent and time independent steps. What is this? This wave equation can be developed both for time dependent and for time independent. It is described by Schrodinger. No problem. Now, time dependent wave equation. What is time dependent wave equation? When the position of the moving particle depends on, or the moving of subatomic particle or wave matter depends on time. That's mean the wave function depends on time. Or clearly if we say, if the potential, that is if the potential energy depends on time, then the wave function or the position of the subatomic particle depends on time is known as time dependent wave equation. And what about the time independent wave equation? The time independent wave equation is that when the potential energy, does not depends on time, then the wave equation or the wave function does not change with time. This is known as time independent wave equation. Time independent wave equation. Now, the wave equation is very important for this time dependent and also for time independent. The time dependent Schrodinger equation, let us consider a Schrodinger or monoatomic. What is this actually? Monoatomic particle, that's mean, or we can say the plane monochromatic wave. Let us consider a plane monochromatic wave moving along, let us consider x direction and represented by a wave equation or a just wave function psi xt. What is x? X is the position and t is the time, equal to a into e to the power I kx minus omega t. What are they? This is a wave function by which we can represent a wave of any matter wave or any subatomic particle. That's mean space-time behavior of any moving particle where angular frequency, what is this? Angular frequency, that is W. Angular ओमेगा बोलते पारी एटाके, W ना बोले ओमेगा ही बोली, equal to 2 pi nu. What was the nu? Nu is the frequency of wave. Nu is the frequency of wave. Nu equal to frequency लिखছি of wave. And what is k? K is the propagation constant. Okay, propagation constant whose value or k equal to, can write 2 pi by lambda, while lambda is the wavelength of the wave or particle. Clear? Now, according to the quantum theory, according to quantum theory, is nu equal to actually E, energy. We can multiply by 2 pi and can divided by 2 pi, h by 2 pi into 2 pi by or nu, that is actually into nu or c by lambda. What happened here? What happened here? Now 2 pi nu, what is this? This is known as h cut. H by 2 pi is h cut into 2 pi nu is actually omega. And momentum P equal to, what is this? According to de Broglie equation, h by lambda, then this is actually h by 2 pi into 2 pi by lambda. So what is this? H cut. What is this? This is k, propagation constant. So momentum equal to, we already proved that P equal to H cut K in this previous lecture. Okay, previous lecture means in postulates of quantum mechanics we already proved P equal to H cut K. Now we want to develop time dependent Schrodinger equation. Now we want to develop time dependent Schrodinger wave equation. For number 1, for free particle, and for a particle which remains in external force or particle under external force, particle under external okay. So at first we will derive a wave equation for free particle, and it is time dependent, and it is also time dependent for particle under external force. Then we will develop another equation, that's been time independent Schrodinger wave equation, and this is all in quantum chemistry. Schrodinger wave equation for free particle. What is free particle? When there is no force acting on a particle, the particle is called free particle. There is no force on particle, this is known as free particle. This free particle has no potential energy also. Free particle, so we can define there is, if or there is no force on particle is known as free particle, or any force on acting on the particle is known as free particle. And why it is free, and what is will be the potential, and there is no force on the particle is known as free particle, and known as free particle, and the potential energy on the particle or of the particle, the potential energy of this particle must be 0. Okay, that is V equal to 0, but it has a constant momentum, clear? এই যে momentum, when momentum is constant, that means mv is constant and momentum is p. As the force acting on the particle is 0, that is F force acting on the particle is 0, then it implies, that means dp dt, that means derivative of the momentum with time equal to 0, অর্থাৎ কনস্ট্যান্ট মোমেন্টামে কিন্তু পার্টিকেল যাচ্ছে, পার্টিকেল মুভিং ইন এ কনস্ট্যান্ট momentum, hence the derivative of the momentum with respect to time must be equal to 0. So what happened here? If it is 0, then the total energy of a non-relativistic free particle, the total energy of non-relativistic what is non-relativistic? That's mean there is no relativity. Okay, non-relativistic free particle of mass m moving along x direction what will be the kinetic energy? The kinetic energy E equal to half mv square equal to m by 2 m into mv square, that is this denominator and we multiply just by m, then what happen here? M into m square, m into v square divided by 2m. Okay, what is this? Momentum. So this is actually p square divided by 2m. So kinetic energy equal to p square by 2m. So p square by 2m, since it is only one direction, that's mean one dimensional, so kinetic energy E k equal to px square divided by 2m. Px means in x direction momentum. Clear? Now if we consider the wave function psi xt, that is in x direction, only one dimensional in space time, equal to a into e to the power I kx minus omega t. This is a common wave function for space time behavior of a particle. Then what happened? If we do a derivative, we get derivative, the first derivative with respect to time, what happen here? Then with respect to time, del t psi, just I write it psi equal to a del t e to the power I kx minus omega I t, clear? Equal to, what will be the value? Just a into e to the power I kx minus omega I omega t into, since this is a time, then x is independent of time, then I omega minus I omega, yes, there is a minus I omega. Actually this is the wave function, so del psi del t equal to, so this is psi and this is minus I omega, this is a psi, okay. So this is the first derivative of psi with respect to time. Now what happens here? If we multiply both sides by I a squared, then I a squared del psi del t equal to minus I omega into I a squared psi, what happens? I into I squared equal to minus 1, that is plus omega a squared psi. What was that? That was the kinetic energy. That was the kinetic energy. Okay. So the kinetic energy E psi. So I a squared del psi del t. This is also well known equation. We already proved it in the different lecture. Clear? Now differentiating both sides with respect to x, what happens? If it is respect to x, then what happens? Then the value will be a into e to the power I k x minus I omega t into, what happens here? I k. That's mean this is also a function, so I k into this part is 0 with respect to x, this is psi, clear? So del psi del x equal to this. Now what happen here? If we do the double derivative, that's mean del 2 psi del x2 equal to what happen? If it is psi, then it will again, this is constant, I will again do derivative on psi, then it will come out minus another I k, that's mean plus k square, again psi will come out, okay. It's I, that will be minus, yes, that will be minus double I, that is I square equal to minus 1. Then what will be the situation? If we multiply by a squared by 2m in both sides, what happened? A squared square by 2m actually equal to into del 2 psi del x2 equal to del x2 equal to a square by 2m minus is there k square psi. K square psi. Why I will multiply it? To gain another equation or to get the kinetic energy actually. Here we know about the K. What was the K? What was the K? 2 pi by lambda. 2 pi by lambda. Now it contains a squared means h by 2 pi. So we can say minus is here, that is minus a squared square by 2m del 2 del x2 psi equal to a squared square by 2m a squared square by 2m into k square psi. Then what is this? Actually this is actually p square. We know a squared k equal to p, a squared k equal to p. Okay, so what was that? P x square by 2m into psi. This is actually kinetic energy, that is E psi. So minus a squared square by 2m del 2 psi del x2. This is another equation. This is a wave function and this is an operator here, and this is a eigen value, this is the eigen function. Okay, and with the derivative of time, that is I a squared del psi del t is equal to also E psi. We get it already. So comparing these two equations, we can say what was that? I a squared del psi del t equal to, or in this way you can say that minus it's minus I a squared del psi del t equal to this. Clear? And this is the time dependent. This is time dependent. Time dependent Schrodinger wave equation for free particle. We can solve this also, but for this time limit we just discuss or we just develop a equation which is known as Schrodinger wave equation for free particle and time dependent wave equation. Now, what will be the Schrodinger wave equation for particle in external force? When and free particle, that's been moving particle, remains in external force field, then its kinetic energy as well as its potential energy will be arise, and its total energy must be equal to its kinetic energy plus potential energy. Before external field, it was only constant momentum was there. For this reason, there was only kinetic energy. Now, in external force field, there must have a kinetic energy, that's mean in x direction. If the particle moving in x direction, then it will be px square by 2m. It is the kinetic energy, plus there must have a potential energy which is known as vxt. Since x is a direction, only one dimensional, we consider at first we consider one dimensional moving of any particle. Now, the total energy must be equal to this, because this is the kinetic energy, this is the potential energy in external force field, because in external force field the potential energy is not zero. Then if we consider a wave function psi xt, then this is a operator. At first this was the kinetic energy operator, now this is the total energy operator. Now px by 2m plus vxt, if we consider a wave function psi xt operates, this operator operates on the wave function psi xt and gives the total energy E and psi xt. Since it is a quantum mechanical operator, its operate on a function gives a eigenvalue with the original wave function. Then what happened? That's mean we already know what was that. That was actually I is cut del t, I is cut del t. This is okay. Sure. Psi xt E was that clear? Now if we consider that E is a total energy, now px square, what was that? Px square by 2m psi xt, it was also that minus a square by 2m del 2 del x2 psi xt. Clear? Psi xt. So this was that. and E is this, then what happened? This plus V, actually V is another operator, potential operator. Then we can write that minus A cut square by 2m del 2 del x2 psi xt plus, because this was the just kinetic energy operator, plus potential energy operator, that is V xt psi equal to this, or you can write equal to I A cut del t psi xt. So there is equation. What happened here? If we consider, or we can take common the psi, this psi xt. Actually, what is psi xt? Psi xt means wave function in one dimensional particle at time t and with position x, and this is actually E psi. So this equal to also E psi. Clear? And this is the one dimensional time dependent Schrodinger wave equation for the free particle. It is the free particle in external force field. Okay. Now what was that? And what was that? Now we can say I is cut del t psi rt for 3 dimension, when r is the coordinate x, y, z, equal to, there was a E. Now we will define is psi r t. What was that? In place of E, we will use is for 3 dimension, and for 1 dimension we can use only kinetic energy E. Okay. And what was that? This is actually the 3-dimensional energy operator. 3-dimensional energy operator in which the kinetic and potential energy both are there, and is the Hamiltonian operator. Is the Hamiltonian operator. X was the 1 dimension, when we used 3 dimension, then this x will be r, this x will be r, this will be r, this will be r, this is r, then this is r, this is r, and it will be s. Clear? So this is the s operator. That's mean minus s cut square by 2m del r2 plus v rt. This is actually s operator, and this operates on psi rt, gives s or E that is actually total energy. Clear? So this is known as three-dimensional wave equation. If we say there is a psi, there is a psi, there is a psi, and if it is H, just H, because H is a wave eigen value, when it is, this is H total, this is H psi, this is cap equal to H psi. There is no cap because this is a energy value. So this is the operator and this is a energy value. So H psi equal to E psi, you can also, it's called E psi, no problem, because E is denote energy, H also denote energy. This is a Hamiltonian operator for three-dimensional time dependent Schrodinger equation for a particle in external force field. Now we may see that which wave function is the Schrodinger equation wave function. There is a problem. Prove that the wave function psi xt a cos kx minus omega t does not satisfy the time dependent Schrodinger wave equation for a free particle. What will be the answer? Answer is simple. I quickly done here. For free particle, the time dependent Schrodinger wave equation is this. We know it. Here the wave function is psi xt equal to a cos kx minus omega t. Now first derivative of psi del x psi equal to minus k ak, this is a, from here k sin kx minus omega t, and double derivative of this equation of this psi actually del x to psi minus a k square cos kx minus omega t. Now what happened? Minus a square by 2m into this equal to minus a square 2m, the minus is just in the opposite side, a k square cos kx minus omega t. Again derivative with respect to time. The first derivative of with respect to time of the psi and multiplying by I a squared, that is I a squared into first derivative of psi del t psi equal to I a squared a omega sin kx minus omega t. Now what happened? We know this and this are equal for free particle. Okay, for free particle without any external field, then in the right hand side of this equation, this one and this one is not same. So we can say that the psi xt is not the wave function or does not satisfy the time dependent Schrodinger wave equation for a free particle. Okay, because this and this equal for free particle, but this equal to this, and here with respect to time this derivative is such this. So these two is not equal. So we can say this type of wave function does not satisfy the time dependent Schrodinger wave equation for a free particle. Thank you.